Hi, my name is Samuel Lee, and this is my Physics 2211 lab number 3, Black Holes and Orbits. So to start with the introduction, the lab had two parts to it. Part 1 was, the purpose was to analyze the motion of a star in orbit around a black hole in order to determine the mass of the black hole. And in Part 2, the purpose of the lab was to calculate the velocity that could achieve a figure-8 orbit around a planet and moon system. Labs like these would be important because simulations like these can help model objects in space and their behavior, and there's a lot of applications that we can have on real-world objects in space when we're launching rockets and stuff like that. So next up, some of the fundamental physics principles explored in the lab. The main two fundamental principles explored in this lab is the gravitational force and Newton's second law. We can see with the law of gravitation that the force of gravity between two objects is equal to g m1 m2 over r squared. This is a force that will change depending on the two objects' positions because of the r squared. Next, Newton's second law comes into play with the momentum principle as well. By using the position and velocity update formulas, which you can see on the slide there, and setting F net over m equal to the parallel and perpendicular components of the force, by using the momentum principle. This is important because the motion here is curving because it involves orbits in space. So next, to discuss the model and the setup, in part 1, the system was the black hole and the orbiting star. We were given the initial mass of the star, and then we had to plot the trajectory of it. We assumed that there would be no work done in the system by any surroundings. Same in part 2, but the system instead was the planet, moon, and spaceship. And then here we can see a screenshot of some of the code from part 1 where we modeled the orbit of the star around the black hole. The F net was determined to be dp/dt, which matches the fundamental physics principles we discussed earlier. We calculated the F net parallel and F net perpendicular using Newton's second law, and then we added those together for the total net force. And here you can see a video of the actual lab, the trajectory of the object, and I'll talk about the results while it plays and cover it. The calculated masses were averaged in a spreadsheet, and the mass of the black hole is determined to be 1.47 times 10 to the 34th kilograms. Arrow vectors, the blue and the pink, represent the parallel and perpendicular components of the force, and the sum of them is the orange, which is the net force. Next, for part 2, here's a screenshot of the code that I used. At the top, you can see some of the initial conditions set for the lab, including the moon's mass and velocity. Under that, the ship's initial velocity in the x and y directions are set. This was found through trial and error and running the program a lot of different times to kind of narrow it down. The final velocities that were used were negative 2,000 meters per second in the x direction and 25,000 meters in the y direction. And under that, you can see the calculations of the net force on the moon. We determined the net force on the moon by adding the gravitational forces from the ship and the planet that they were exerting on the moon. And a similar process was done for the spaceship to calculate the net force and then the trajectory of that. And here's a picture of the results from part 2. You can see that the spaceship doesn't just orbit the moon or just orbit the Earth. It makes it's kind of a figure-8 orbit, right? I had to set the time to 1,000 hours because it was taking a long time. But from the results, you can see that it's very difficult to achieve a stable figure-8 orbit when there's 3 objects in the system. Thankfully, the planet wasn't moving because otherwise we'd have like a 3-body problem. And in both of these programs, there's simulations, right? So to talk about something like the error, there wouldn't really be an error in the calculations of the programs since everything was done through GlowScript, but it's very possible that the results here wouldn't match a real situation in space. The reason behind that is because in space there's a lot of other different objects in the surroundings that would exert forces on the system. And there's always the chance of human error in the lab as well, in some steps, and then trial and error were used to find the velocities in part 2, which is not a very efficient system, and there's most likely a better initial condition for the velocities. But moving on from that, we can go into the what if and what does it mean questions here. As for the what if question, if we wanted to predict the entire system, we need to consider the forces that the spaceship and moon exert on the planet as well, and update the position and the velocity at each increment. And the force that the black hole would exert on all the other 3 objects as well. Because of the mass of the planet and the black hole, the planet would be higher than the moon and spaceship, but the black hole is much more massive compared to the other 3. So it's very likely that the black hole would contribute most of the interaction. And then talking about the rate of change of momentum, the rate of change of momentum is basically net force, right? If you want to look at something that you can kind of measure or observe, you can see that if it's accelerating, you can infer that there's net force on it. So basically, you can kind of see how momentum changes and look at the interactions that the object has with its environment. You can determine things like the net force. In conclusion, both models are programmed in GlowScript, and based on the experiment, we can draw these conditions that the mass of a black hole can be calculated based on the orbit of a star if we know the mass of the star, and that the figure 8 orbit is very difficult to achieve in a system because the initial parameters or the velocities are very difficult to find out. Thank you.